Okay, I'm going to get started on section 9.2 now. 9.2 is called rational exponents. I have a bunch of laws of exponents that we should know. We should have all been there and done that before with these laws. We will need to know the laws of exponents for various things in this section and even beyond. So if I just quick go through these, if you're multiplying and you have the same base, you're going to keep the base and add the powers. If you're dividing things with exponents and the base is the same, you're going to keep the base and subtract the exponents. Okay, a to the m to the nth power, you're going to multiply the powers there, it'd be a to the m times n. In these two laws, so whenever you're multiplying or dividing things inside the parentheses, you can bring the power into each and every term, okay? Now, careful with that one, because you can only do that if you're multiplying or dividing, never ever if you're adding or subtracting. 1 to any power is 1. Anything to the 0 power is 1. Okay, as long as the base is not 0, which we won't have to worry about. Sometimes we work with negative exponents. Okay, a to the negative n is the same as 1 over a to the n. Okay, if we want to rewrite that with a positive exponent, we'd use this law here. And then the new law in this list would be right here, the law for rational exponents. It says, let m and n be integers with n greater than 1. Okay, then a to the power m divided by n in radical form would be the nth root of a to the m, and you can also write that as the nth root of a, whatever that is, and then to the nth power. This form would probably be a preferred form just in general because, depending on the values of a, m, and n, sometimes, like if you're working with large numbers, it might be easier to just do the nth root of a first. Since a to the m is going to be a bigger number than a, you can just do the nth root of a first, and whatever that is, then raise that number to the nth power afterward. Okay, I'll comment on that again once we look at some examples here. But all right, so let's get some practice using the law for rational exponents, and with some of these other ones mixed in. Problem 12, we want to rewrite each expression as a radical expression and then simplify if possible. Assume that all variables represent non-negative numbers. Okay, so x to the 1/2 means that m is 1 and n is 2. Now, an index of 2 means that you're working with a square root. So x to the 1/2 would be the square root of x to the first, or just the square root of x. If I wanted to know 9 to the 1/2 power, well, that's the same as the square root of 9, which I know is 3. Okay, so I'd want to think of that in radical form in order to get the answer. Okay, x to the 1/2 is the same as the square root of x. X to the 1/3 would be the same as the cubed root of x. So like if I wanted to know 64 to the 1/3, well, that's the same as the cubed root of 64. Okay, and I know the cubed root of 64 is 4. Since 4 cubed gives me 64, right? If I take 4 times 4 times 4, I get 64. Negative 64 to the 1/3, okay, well, that'd be the same as the cubed root of negative 64. Now, you can take the cubed root of a negative, that's okay. You just get another negative in return. It'd be negative 4 here, because negative 4 cubed gives me negative 64, right? If I take negative 4 times negative 4 times negative 4, I get negative 64. Here's negative 64 to the 1/3. Well, the negative would have to stay in front of the radical. 64 to the 1/3, we've already said, is the same as the cubed root of 64, right? So I'm looking at negative the cubed root of 64. That would also give me negative 4. Now, of course, one thing that I want you to observe here is the parentheses are on one expression, and they're not over here, but you get the same answer in this case. Okay, now in another situation it would make a difference. So like if I wanted to know negative 64 to the 1/2, well, 64 to the 1/2 would be the same as the square root of 64, but I've got a negative in front of that. The square root of 64 is 8, and so -8 would be my answer. Now, if I had parentheses, -64 to the 1/2 means that I have the square root of -64. Okay, since -64 would go under the radical then. You can't take the square root of a negative, that's not a real number, right? So that's the point that I was making here. Sometimes the parentheses wouldn't affect the result, okay? Like it didn't affect the result here, although the calculation was done differently, right? Because on one of these, the negative was underneath the radical, and on the other, it was in front of the radical. But in other cases, like it would make a difference, okay? In terms of getting the right or wrong answer, like it would make a difference here. -1 to the 1/3, that's the same as the cube root of -1, which would be -1. There's a little note down here. It says, make sure to reduce an exponent if possible, okay? If you don't reduce the exponent, that can be a problem. And I'm just kind of showing you an example here of how that would be a problem. So -1 to the 1/3 is -1. We just said that. If I had -1 to the 2/6, well, 2/6 reduces to 1/3, right? So I should read that statement going this way. Okay? Now, -1 to the 2/6 can be written as -1 squared to the 1/6, right? By my rules of exponents, I would just multiply these powers together. That's law 3 in this list here. And so 2 times 1/6, that'd be 2/6. -1 squared is 1. 1 to any power is 1. Okay, so if I were to work the calculation by not simplifying the exponent, I would have a wrong answer. Okay, so the point of this work here is to say that, if in the situation where the exponent reduces and you don't reduce it, you could be led to a wrong answer. Okay, of course, 1 does not equal -1. That's not a true statement, right? But the point is that we don't want to be doing the calculation from this point on to the right. Okay, otherwise we'd be misled. Always reduce the exponent if the exponent reduces, and then continue the calculation. Okay. Let's take a look at problem 13. We want to rewrite each expression as a radical expression and then simplify if possible. Okay, so part A, 8 to the 2/3. I'm going to be using this law for rational exponents. M is 2, N is 3. So I'd have the cubed root of 8 squared, and that's what I've got written here. 8 squared is 64, and the cubed root of 64 is 4. So 8 to the 2/3 would be 4. Another way that you could have worked this problem is you could have used the alternate form here. Okay, M is 2, N is 3, and so I could have found the cubed root of 8 first, and then raised that number to the second power. Okay, the cubed root of 8 is 2, and 2 squared is 4. So either way, I still get the same number. So it wouldn't really matter, which form I used in this problem. I'd still be getting the same. In general, you always get the same answer. Okay, but in some cases, we want to be using this this alternate form here at the end rather than the form before it. Okay, here's maybe a better example of what I'm trying to say with that. So, if I wanted to find 9 to the 5/2. In this law, so A is 9, M is 5, and N is 2. Now, an index of 2 means that you have a square root. So I'd want to look at this as the square root of 9 to the 5th. Now, if 9 to the 5th is underneath the square root sign, 9 to the 5th is a really big number that I don't know off the top of my head. I'd need a calculator for that. So it would be easier for me to look at this alternate version where I just simply take the square root of 9 first, and then I raise that number to the 5th power. I know the square root of 9 is 3, and 3 to the 5th would be 243. Okay, so the calculation becomes way easier in terms of mental math if I use this alternate form rather than the form before it, because like I said, I don't know what 9 to the 5th is off the top of my head. I know it's a big number, and then whatever number that is, I then need to know the square root of that. Okay, so that kind of makes the problem more difficult than what it needs to be. So if I were to do the problem like that, I'd still get the same answer. Okay, it's just I'm making it more difficult than what it needs to be, though, because I'm working with bigger numbers, though. So be careful about that. Like this alternate form is kind of a preferred form, usually. Okay, here's another one. Part C, 64 to the negative 2/3. Well, let me use law 8 in that list here to begin. I'm going to rewrite that so that we have a positive exponent. 1 divided by 64 to the 2/3 gives me that positive exponent now. And then I'll need to know what 64 to the 2/3 is. Okay, well, let me use my law for rational exponents here. A would be 64, m is 2, and n is 3. Okay, and I'm going to rewrite that now into a radical form using this law. And you can see I've done that here. Okay, it's going to be the cubed root of 64 squared. The cubed root of 64 is 4, and 4 squared is 16. So 64 to the negative 2/3, that's the same as 1 over 16. Okay. Now, like everything else that we've been doing, keep the answer in exact form. We don't need to run to a calculator and type this in. We'd get some infinite decimal that we'd have to round, and it would no longer be exact, and it would be wrong then if they were looking for an exact form. So be careful about that. Now, in some of the problems that you will need to use a calculator, okay, it's not a lot. I mentioned that in an earlier video. Okay, so keep that in mind when you're doing the work here. Try to be doing the calculations without a calculator. Okay, that's kind of the intent of everything really in this chapter. Okay, I would say don't use a calculator unless you're told to use a calculator in the problem. Let's take a look at problems 14 and 15. Use a calculator to approximate the cubed root of 5 to the nearest hundredth. Okay, so we looked at how to work with square roots earlier. Okay, what if you have a cubed root? Okay, like I don't see a cubed root button on my calculator. Now some actually do have it. Like on this model, if you were to hit second and then the caret button, it sets you up with a form where you can enter in an index. And so like I could type in the cubed root of 5 and hit enter. Okay, and I get 1.71 if I go nearest hundredth, they said, nearest 2 digits. Okay, now what if I didn't know about that? Okay. Well, I'd want to know this law of rational exponents then. Okay, the cubed root of 5 in a rational exponent form would be the same as 5 to the 1/3 power, right? X to the 1/3 is the same as the cubed root of x. So the cubed root of 5 would be the same as 5 to the 1/3. And, okay, I've got that written down. Now, my calculator can do exponents, right? Any calculator can do exponents. So like I could type in 5 to the power 1/3. And of course I'd want parentheses there so that the 1/3 is entirely in the power. Hit enter and you still get the same result. Okay, 1.71 if you go nearest 2 digits. Now on my graphing calculator, I don't have an option like you saw in the other model where I can do radical calculations with an index of like 3 or 4 or 5. I don't have a cubed root button. I don't have a 4th root button. I got a square root button. So like on this model, like I'd want to be familiar with that law of rational exponents. And I could type in 5 to the power 1/3, which is the same as the cubed root of 5. Hit enter, and that's how I get my answer there. Here's another one. How about the 4th root of 378? Okay, so if I type that in, it'd be 378 to the 1/4 power. Be sure that you include the parentheses around the power. That way your calculator knows to keep 1/4 entirely in the power. And okay, nearest hundredth, it looks like I'm getting or nearest thousandths, I guess, on this one. 4.409, roughly, if you round to the nearest 3 digits there. Okay, and of course, since there is rounding, we'd want to use the approximation sign, not the equal sign, since these are not exact numbers. Okay, here's the exact form. Okay, this is an estimated form or an approximate form. Okay, we'll stop right there.